Hello again, everyone. Welcome to session 4 of the Think Like a Physicist Clematis training program. I'm Sapu, a PhD student at University of Oxford, and I'm very excited to be here with Libby, who will be leading the session today. So Libby, as you might know, is a fully funded PhD student at the University of Sydney, and she received a Fulbright Pearson Scholarship at the University of Toronto, which is where she did her undergraduate in physics and astrophysics. Her current work in her PhD focuses on developing a new class of efficient plasmonic and nanophotonic devices. Today, Libby will give us an extensive introduction to photonics and plasmonics, and we will be exploring how to enhance nonlinear light-matter interactions through nanoscale photonic and plasmonic structures. When I learned of this, I actually didn't know a lot about photonics and plasmonics, so I personally am very excited for the session. And if you didn't know, photonics and plasmonics are actually used in wide-ranging applications, from supercomputers to lighting, manufacturing, security, healthcare. So I think understanding the principles of physics behind photonics would be very cool and very insightful. So thank you again, Libby, for being here. Let's get started.
So first of all, thank you everybody for coming. And today's session, as it was just mentioned, will focus on photonics and plasmonics. Okay, so we're gonna first start this session by going over a bit of the motivation of why do we even care about photonics and plasmonic systems. Now, we're not gonna cover all of the fields that they're applied to, as we were just told. But Shamrock, there's a lot of applications. We're just gonna have a few. We're just gonna see a few. Then we're going to go over a bit of review of optics, so a few concepts that have been covered in previous sessions and others that might be new to some. Then we're going to jump into the world of nonlinear optics by going over a few of the nonlinear optical effects that we're going to need to understand the paper that we're going to see at the end. Then we're going to go over a bit of concepts in photonics and also plasmonics, so understanding the difference between these two types of systems, as well as what limit, so advantages and disadvantages. And finally, as I just mentioned, we're going to cover a scientific paper, not the entirety of the paper, but a bit of it. And just to give you a taste of what we're going to be seeing, this is the paper, and the title is Fundamental Limitations to the Ultimate Kerr Nonlinear Performance of Plasmonic Waveguides. Now, I'm sure that some words such as, for example, Kerr nonlinearities and plasmonics might not be something you're familiar with, but I hope that by the time we actually reach the point that we go through the paper, you will be able to understand what's going on here. Now, as I just mentioned, we're going to start by going over a bit of the motivation. Okay, so for that, I'll share with you something that's called Moore's Law. Now, all this law tells us is that throughout the years, as time passes, there's going to be an exponential growth in the numbers of transistors that we need. Okay, and transistors, for those of you not familiar with, transistors serve as the fundamental building blocks for electronic circuits. Okay, so as time passes and the processors or the electronic components that we have get chips, for example, get more complex, you need more transistors. And overall, just wrapping up with this, we're seeing an exponential growth in the need for computer capabilities when it comes to electronics. And at some point, this growth is not going to be sustainable and electronics will run out of steam. So electronics on their own will not be able to meet the demands for high-speed or ultra-fast processing communications that we're demanding. And taking this into consideration, I'm going to ask you guys, what other ways can information be carried? So aside from using electronic circuits, what other ways can be done to carry information? So for this, maybe you want to think about the title of this presentation, if anybody wants to try and answer.
So just to repeat the questions, what other ways can information be carried? Someone answered in the chat, magnetic field.
Yes, so technically, yes. So think of not only magnetic field, but what other fields do we know about? The combination of that plus not only magnetic. Yeah, so light-based communications, yeah. So pretty much, I was searching for somebody say light. So yes, I said yes to magnetic fields because remember, light is an electric magnetic wave. So you were half there with the answer. So that's great. Thank you guys. So light. Now, light-based communication. So in order to pick up the slack or go further into ultra-fast types of data processing, we can use light. Now, I'm sure some of you have heard of it, for example, free space optical communication, or even something more common, such as, for example, optical fibers. So those are ways that we can apply light-based communications. Now, how we actually get this is through photonic systems, so photonic chips and different types of other photonic systems. Now, in order to get the part of the ultra fast, so I'm saying that we need nonlinear effects. So we need nonlinear optical effects to enable this ultra-fast signal processing. So through this presentation, I'm going to be talking about photonics and also plasmonic systems, and we're going to be using the systems to exploit the nonlinear effects that are going to enable us to actually get this ultra-fast signal processing. So this is a bit of the motivation behind photonic systems, and I'm sure most of you have heard the word photonics before. Now, when it comes to plasmonics, I know that this might be a newer term. Okay, so most more unfamiliar term. Now, plasmonics is inspired by photonics. And I will explain what plasmonics is now, but without explaining what it is right now, I'll just tell you that plasmonic systems will allow us to have compact and ultra-fast devices capable of exploiting optical nonlinearities, okay? And the keyword here is compact, okay? So that is what a plasmonics brings into the picture with additionally being able to exploit nonlinearities. And in order to see where this is actually applicable, I'm going to ask you guys to, I want to guess if you can guess where this would be needed. So where do you need really compact devices or really compact parts that are ultra fast? And for this, I also ask you as a hint to think of the fastest type of computers that we have. So if anybody wants to answer in the chat, what are the fastest computers that we've been able to create?
Question is, can any one of you guess where compact and ultra-fast devices would be needed? And the hint is think of the fastest types of computers. Any ideas?
Yeah, that's a great answer. So, and I was looking for anything supercomputer, quantum computers, anything in the realms of quantum computing. And now, specifically, Plasmonics has applications in this realm. Okay, so because it's able to make things even more compact, it is really beneficial when it comes to quantum computers when you need things that are really small and able to actually do the computations at ultra fast speed. Now, with that said, let's move on to a bit of an optics review. Now, as I said, some concepts might be a bit of review, some might be new, but we're still going to go over them just in case. So the first one being that light has a dual nature. Light has properties of a wave and of a particle. Okay, so the particles, as we know, are photons, and the waves are electromagnetic waves. Okay, so that then we know that light diffracts, and specifically in the first session of the series, we covered the fact that there's something called a diffraction limit. That means that the closer two point sources are, the harder it is going to become to tell them, identify them clearly, no matter how much you zoom in, because light diffracts. And with that, I mean that when you have a point source, you're going to see this other point of intensity that form around the pointers. When you get closer and closer, this is not going to allow you to tell the 2 point sources apart. So you cannot infinitely zoom in just because of this nature of light. Okay, so that's something just to remember. Now we're going to introduce the concept of refractive index. Now, as a crude definition, the refractive index is the ratio of light speed in a material to its speed in a vacuum. And what I mean in a vacuum is when light travels when there's nothing, so no air, no other particles. So that's what we refer to as a vacuum. But another way to think about the refractive index is that it's a value that is pretty much just telling us how much light bends when it enters a new medium. And here on the slide, we have a little example. As you can see, when light propagates through a medium with a different refractive index, so N1, it is not going to travel in a straight line, but it's going to be slightly bent, okay? So that is the concept of refractive index. Now, thanks to this property of light that it refracts, we're going to be able to have something called total internal reflection. Okay, so when you meet the conditions of refractive index, in this case, the core having a higher refractive index than whatever material surrounding it, we usually call it cladding or whatever is surrounded, we're going to be able to guide our light. Okay, so instead of the light just going out as it does in this example, it is going to reflect inside. So it's going to be confined to the space of our core here. So that is the principle of total internal reflection. And with that, we're able to create waveguides. Okay, so waveguides, pretty self-explanatory, I think, just something that allows us to confine light to space and direct it however we want to. Okay, and in waveguides we have different modes. So here, just to give you an overview of what's happening, the representation that I have here could be, for example, one type of longitudinal mode. I'm sure some of you have seen optical fibers. So here we have another example of a mode. So this is a single mode, just like pretty much how light is traveling through our core here. Here's a straight light. And if we cut a cross section, we're able to get a transverse mode. Okay, so this is a transfer mode of the electromagnetic field that we're seeing. Okay.
We have a question
Sorry,
in
this
the
is the
chat.
question. Yeah.
So for the previous slide, what's
Yes.
N1 and N2 referring to?
That's referring to those different types of refractive index. So when N1 is one type of refractive index of a material, so in that case, I think it was, yeah, so N1 would be the inside and N2 here outside. Sorry, I switched the values here. Sorry if that was confusing. But yes, that's just referring to different types of refractive index, different values. Hope that answers the question. Now, waveguides are not only optical fibers, but they can also be integrated to a chip. So here, for example, we have a really nice representation where we have an optical fiber that is allowing us to couple light into this other waveguides that are integrated into a chip. Now, this is usually called a photonic integrated chip or a PIC. And as you can see, we can do a lot of things with these waveguides. Now, I'm not going to cover all of them. More than happy to talk about it if anybody's curious at the end of this presentation. But with that said, let's move forward. Okay. Now, something that we really care about is how light interacts with matter, okay? And when we have a waveguide, as I told you, light is going to propagate through our core here, and it's going to interact with the molecules of whatever the material that we have here is, okay? Usually, if you have just a regular power beam, you just pass it through, nothing is going to happen to our wave of light. The input wave is going to be the same as the emitted wave, okay? But now, what if we increase the intensity of the laser beam? So what if all of a sudden we put in a really high intense beam into our core here? What will happen? Now, in order to answer that, I'll ask you guys to think about this. What happens when an electric field is applied to a dielectric material, such as an insulator? Okay, so here we have our dipoles, we have our dielectric material. What will happen to the charges here if we apply an electric field?
The question is what happens when an electric field is applied to dielectric materials? So you induce an electric field by putting the opposite charges on the two metals, right? In other words, I think the question can be rephrased as what happens to these charges, right? The plus
Yeah,
and
so what's gonna happen to these charges when you apply electric field?
let's give it a moment.
Yes. Yeah, so the charges will align as Tano has said. So here we have here, as you can see, when we have an electric field applied, we're gonna have an induced polarization because our charges here are gonna align the negative with the positive and the positive with the negative here, as you can see. They're all gonna be pretty much separated if you want to think of it that way. So this is what happens when you have an electric field applied. Now, I want you guys to remember that light is an electromagnetic wave, so it has part of an part of it is an electric field. Now, if we input a really intense wave of light, we're pretty much propagating a really intense electric field. That is going to induce polarization within our material, which is ultimately going to lead us to a change in our emitter wave. So the light that's coming here is going to induce polarization within our molecules here of our material, of our dielectric material, and it's going to generate a wave that has a different frequency, okay? Now, this is what we're going to call a nonlinear material, something that allows us to actually get this different, in this case, frequency, okay? That is the basis of nonlinear optics. Now, in nonlinear optics, we specifically see the nonlinear relationship between the applied electric field and the induced polarization. Okay, that leads us to different types of effects. For example, the one we just saw is analogous to what is known as second harmonic generation. Then we have something, for example, called self-focusing. I think pretty self-explanatory, but happens because the change in refractive index in our material is changing, which is going to bend light such that it focuses when it comes out, in this case, of our nonlinear medium. Now, we're specifically going to focusing on the Kerr effect, but before doing that, I just want to remind you guys that it is through the optical nonlinearities that we can achieve the goal of faster or ultra-fast signal processing, right? So at the end of the day, we want to harness this effect in order to get our really fast processing platforms, okay? So as I mentioned, we're going to focus on the Kerr effect, and I'm sure some of you remember it from the title of the paper we're going to be covering. And pretty much it can be summed up as being the change in refractive index caused by an electric field. Okay, so what do I mean with that? For that, we're going to look at this formula here, which is the induced polarization. Okay, and just to make sure we're all on the same page and everything's fine, polarization of a material when exposed to an electric field. So this is the type of polarization I'm referring to. Just as we saw in the previous example, when we have an electric field that is applied, the positive and negative charges in the material are going to be separated. Okay? And here I just want to show you that if we disregard this higher order terms, we have our polarization and electric field component and that's an electric field component. So I'm going to explain what this is in a minute. So our X is here, or chi in the Greek alphabet. But I want you to see that if we disregard the higher order terms, you have a linear relationship between your polarization and your electric field. Now, we actually have these other terms that I just mentioned. This are the Greek letter chi, or we're just going to call them the susceptibility terms. Now, all they do is they describe material's response to an external electric field. Okay, so the higher they are, the higher effect you're going to have based on your electric field. So the higher nonlinearities in the case of these terms, which are the nonlinear polarization terms. Now, as I just previously mentioned, if we were to ignore these higher order terms, which are the nonlinear polarization terms, we would have our normal linear polarization, induced polarization. Now, the linear polarization gives rise to the linear refractive index, which is the same that I just explained at the start of our optics review, but these higher terms will give rise to something known as the nonlinear refractive index, okay? And specifically, chi3. Now, chi2 here will give rise to other different types of nonlinear effects, but we're going to focus on chi3 here. So the nonlinear refractive index, all I want to show here is that it's proportional to this chi3 value, okay? And specifically the real part of it. The imaginary part of this value is linked to the nonlinear absorption coefficient, but we're not going to cover that right now. And this is related to the change in refractive index, okay? So our nonlinear refractive index is proportional to our change in refractive index, but it's also proportional to intensity. So higher intensity means you're going to have a graded nonlinear effect. That's why at the beginning, I told you in the specific example we saw, I told you that by increasing the intensity, we're able to get a nonlinear response out of our medium. Okay, now I want to show you this plot here, first of all, because there's something weird, there's something interesting happening in the axis, and just to give you an understanding of how much nonlinear effect we actually get from types of materials. So for that, I'll ask you the question, do you guys notice anything weird about the two y-axes that we have? Anything that's worth mentioning?
If you look at the figure, is there anything interesting about the two y-axis? What do you observe? Are there any differences?
Yes, that is true. One is nonlinear and the other is not is linear. That is true. Think of the not so much of you can think of the like the magnitude. Just mention one little thing. Yeah, exactly. Yeah, the magnitudes. That's exactly what we're looking for. So yes, as you can see, the nonlinear refractive index is orders of magnitudes below of the linear refractive index. And here you might see some materials some that you recognize, for example, diamond or silicon dioxide here. Now, believe it or not, silicon is considered to have a high nonlinear refractive index. So whenever I say high nonlinear refractive index, I am talking something within the scales of 10 to the negative 16, 10 to the negative 17. Yeah, nonlinear refractive index. So that is just to give you an idea of how small these nonlinearities have and why so much work is done to enhance them. That's why we actually have to put so much work to enhance the nonlinearities. It's because they're really small. Now, at this point, I'm just going to take some time to make a few notes. Now, all materials intrinsically have nonlinearities, okay? But not all materials are good nonlinear mediums. As we just saw, there's some materials that have really low nonlinearities, while others that have really high nonlinearities. Overall, we can see that there's a linear relationship between the linear effective index and the nonlinear effective index. There are a few materials that are not going to obey this rule, such as these two are just nonlinear synthesized polymers. But in general, you're going to have this relationship. Okay, so just have to keep in mind that although you can get nonlinearities in theory from all materials, you will not, well, almost all materials, you will not get really good nonlinearities from all of them. If that makes sense. Another thing that's important to consider are propagation losses. Now, you can have a really good nonlinear material, high nonlinear refractive index, and high susceptibility, but it can lead to higher losses in your waveguides. Now, here, this is an example. So as you can see here, I specifically want to focus on the second part here, where you can see you're trying to couple light into a waveguide, but so much of that light, so much of the actual electric field is getting lost, okay, as it gets propagated. Some will get out, but it is not efficient. So you also have to consider absorption and different types of losses that you get through propagation. Another thing that it's important to consider is the fact that materials have a power threshold above which they will get damaged. So you cannot infinitely just you cannot just infinitely throw light or a really high intense beam into a material thinking you're going to get really high change in non-linear effective index, because you're going to damage a material before you even are actually able to extract what you want, which is the nonlinear effect. So that is something that always has to be considered, especially in experimental work. Sometimes when it comes to simulation or numerical analysis, it can be disregarded, but it's really important if you want to put things into practice. Okay, so with that said, we're moving on to photonics and plasmonics. Just a bit of a review and kind of a recap of what we've said. Okay, so first of all, I just want to make one thing clear. Optics and photonics, you might have heard these terms used interchangeably in some cases. Optics is a wider field. Okay, so optics includes geometric optics, quantum optics, and everything. Well, photonics is a subfield of optics. And in general, when we think about photonics, we think about things such as, for example, optical fibers or waveguides. All of these components are in the micron/nano scale. So we're talking about really, really tiny things. Okay, and such as, for example, when I told you here about the photonic integrated chip that we saw before, right? These are integrated waveguides in chips that are smaller, as you can see here, very, very small compared to, in this case, a coin. But in general, this is the size that we speak of when we speak about photonics. Also, the name kind of gives it away. We're studying light at a photon level, so how that photon interacts with matter. Okay, so that is just to say. Now here, I'm going to be comparing photonics to electronics. This is going to be a bit of a recap since most of the things here we've already mentioned regarding to photonics, but just to make a comparison and see a bit of analogous terms. Okay, so first of all, in electronics, you guide electrical charges, right? So your electrons are your carriers of information, where in photonics, you guide light particles, right? So your photons are what actually are carrying the information that you need. In electronics, we have electronic circuits, right? Now, there's also some types of nonlinear relationships in electronics, of course, not the same ones as the ones that I explained. Those are optical nonlinearities. So, but in general, you have your different electronic circuits and you're guiding your electrons through them. Now, in photonics, we base everything out of total internal reflection, as I just mentioned, right? The fact that we're able to guide light within a material by making sure it stays inside. So thanks to total internal reflection, that is possible, and we are able to have our waveguides. Okay, now when it comes to materials, in electronics, most electronic systems are made out of conductors such as metals and semiconductors, for example, some types of ceramics. Okay, while in photonics, you use semiconductors and dielectric materials. Now, in photonics, you do not use metals. Okay, so that is one of the main differences. You are using mainly dielectric materials. And I guess at this point, I should mention, usually the dielectric material, well, the dielectric material will be your nonlinear medium in photonics. Okay, so now we're gonna go over the advantages and disadvantages of each type of system. Now, the first thing, the good thing about electronic systems and why we actually keep using them, although I pretty much at the beginning told you that they are starting to run out of steam, is because they're cost efficient and compact. Okay, keep that in mind. The major disadvantages are the high propagation losses. Now here, I just want to really emphasize this because whenever you have metals, you're going to have ohmic losses, which are just losses because metals have resistance. Okay, so you're going to have higher losses than you will if you do not use metals. Aside from that, they have a limited bandwidth, meaning that they are limited in how much information they can carry. Okay, so that's not very good when it comes to electronics. Now, going on to photonics, the main advantages they have is that they have much lower losses, mainly because there's no metals involved, and also faster signals. Now, photons in our photonic waveguides are not going to travel specifically at the speed of light in vacuum, but they're still going to travel much faster than an electron, mainly because they are photons are much lighter than electrons are, of course. Now, when it comes to disadvantages, the main disadvantages of photonics is that they're not as compact as electronic circuits, and also a bit more complex to fabricate. But I want to emphasize that they're not as compact as one would actually want them to be. And at this point, I'll take that opportunity to ask you, why can photonic waveguides be made smaller or like made more compact as electronic systems? So what's stopping us? And for that, I'll, as a hint, ask you to think about the wave properties of light. So what property of light prevents you from making the system smaller?
So the question is, why can't photonics waveguides be made as compact or small as electronic systems?
Think about one of the properties of light that we saw at the beginning when we were doing the optics review. What is something that limits light from, well, yeah, I don't want to give it away. Don't think that complex. Think of more like more simple definitions. I mean, in principle, it's not something very complicated. It's something that we saw, just a property of light, um, that we saw at the beginning of this presentation. So think of what prevents you from zooming infinitely if you have two point sources of light together. Yeah, exactly, diffraction limit. So because of the diffraction limit, the size of your waveguide will be always confined to being about approximately 1/2 of your wavelength. So you cannot make something smaller than that. Otherwise, the light is not going to get coupled into your waveguide. So then there's no sense in having that waveguide. Okay, so if we plot where photonics and electronics stands in regards to operational speed and the size of your device, so how compact you can make it, electronics would be here. So it has slower operational speed, but it allows you to make things at a tens of nanometer scale, okay? And for photonics, it would be up here where you cannot go really, really small, mainly because remember in photonics, sometimes one of the main applications would be telecommunications, right? And if you want to be at a telecommunication wavelength, which is around 1.5 microns, you cannot make your waveguide smaller than 750 nanometers. Okay, so that's why photonics is limited by that. And in terms of photonics, although it's limited in size, it will allow you to have higher speeds. And remember, higher operational speeds for photonics means that you're able to exploit higher nonlinearities. Okay, so we can think of it that way. So ideally, what we want, right, is something that has higher operational speed, but that can be made compact. And here's where Plasmonics shines in. And I know I've been saying Plasmonics this, Plasmonics that, but now let's actually see what is Plasmonics. Now, in a Plasmonic waveguide, you combine metal and dielectric interfaces, okay? So this is one of the ways that you can create a Plasmonic waveguide. You have a metal, dielectric, metal, okay? Now, before we had our photonic waveguides, where I'm telling you that here we have a laser beam and it's propagating through the core, okay? Through the core. This can be, for example, silicon, or it can be air, and the silicon can be here, your walls, okay? But it is going to propagate through our nonlinear material. Whereas in plasmonic waveguides, it's not going to propagate through the center of our dielectric/nonlinear material, but it's going to propagate at the interface of the dielectric metal surface that we have here. So how is this possible? Well, this is possible because there's something called plasmons. Now, plasmons are oscillations of the electric field, okay? Oscillations of electrons. And what's going to happen is that when you have a metal, dielectric and metal interface, in your metal interface, you're going to have this clouds of electrons. And they're just going to oscillate up and down, okay? And oscillation of electrons is going to generate an electric field. in the through the surface. Okay, this is what is called as surface plasmons. Okay, so just the oscillations of electrons that generate an electric field. Now, our light, when we input a laser, like a laser light through this, so we input an electromagnetic wave, what is going to happen is that light will travel by coupling to the oscillation of electrons, okay? This is going to couple to the electric field that you see generated here. Okay, so in this case, we have just one photon that's coming, and it's going to travel by coupling to our electric field oscillation here. Now, how is this actually just being confined or maintained within our dielectric medium? That is because metals have negative permittivity, which means that there can be no propagation of the electric field inside the metal. Okay, so when the electric field tries to propagate, it's going to be quickly attenuated. Okay, now when we couple that to our surface plasmons, we have what are known as surface plasmon polarigens. Okay, so that is how light is traveling in our plasmonic waveguides. Okay, so here just a bit of a recap to see what's happening. So surface plasmons are what are going to guide light along this interface. So that's how we are confining light in this type of waveguides, whereas in photonics, light is guided by the principle of total internal reflection, which confines light to the core. Okay. Now, these dielectric materials can be the same, but as you can see, light is not propagating the same way. Now, the advantage of this and why we're actually be able to make more compact plasmonic waveguides is because surface plasmon polarigens or surface plasmons have shorter wavelengths, meaning that you can have higher local field intensity. So you're able to make things smaller because you're not longer dealing with light, the wavelength of light, but now you're dealing with the wavelength of surface plasmon polarigens. Okay. Now, I just want to take a moment to make sure that we're understanding the geometry of the waveguides that I'm talking about. So far, I've been pretty much making reference to slot waveguides, where you have a material that is sandwiched in the middle by two walls. You can think of it that way, the core, and usually in fiber optics, we call this a cladding. In this case, we're just going to call it the material that's sandwiching our dielectric/nonlinear medium, okay? But aside from slot type waveguides, we also have other types of waveguides. In this case, I'm just showing you here, we have strip waveguides and photonic crystal waveguides. Now, I'm not going to go too deep into photonic crystal waveguides since I would ask you guys later on to actually explore how this actually works. But let's take a moment, let's diverge a bit from our slot waveguides and let's look into strip waveguides. If we're talking about purely photonics, the material that you can see here, so this light blue material, is usually going to be silicon. Okay, so silicon is going to act as our dielectric material / nonlinear material, which is going to allow light to propagate. But when it comes to in plasmonics, we're going to need a metal interface. Okay, so here we have a combination of a metal interface, a metallic waveguide with a dielectric waveguide. Okay, and this spacer here is going to be useful because it's going to allow us to see how we can oscillate between a plasmonic and a photonic waveguide, okay? And fun fact, if you actually have the spacer at the right height, you're able to create something that's known as a hybrid waveguide between plasmonics and photonics, also known as a hybrid plasmonic waveguide. That's a whole different story. I'm not going to cover it. I just wanted to mention because I thought it's really cool. So here we have a figure that is showing us the different size that you can hold depending on how thick your spacer is. So now remember, your spacer is this layer that separates your dielectric waveguide with your metallic waveguide. Okay? If the spacer is non-existent, so if it's high to 0, you have a plasmonic-like waveguide. And as you can see, light is traveling in the dielectric part, but at the interface between the metal and the dielectric. Okay? Remember, this is just a cross-section of our strip waveguide. Okay? If you start increasing the spacer's height, as you can see, all of a sudden our light is no longer propagating at the interface, but it is getting into the spacer, okay? And if you keep increasing the height here infinitely to the point that you no longer have a metallic part, you get a photonic light waveguide. As you can see, light is propagating at the center of our dielectric material here, okay? Now, their hybrid plasmonic waveguides, I could just quickly mention them, would be something like C here, so the figure C here, where light is propagating through the spacer. And if anybody's curious and wants to, by any chance, learn a bit more of hybrid plasmonic waveguides, this is the paper where the figure came from. I think we're able to share the paper with you through the chat, but just to give you a bit of a sneak peek, hybrid plasmonic waveguides attempts to combine the best of both worlds. So the advantages of photonics and the advantages of plasmonics to even have better nonlinear effects. Okay, so with that said, though, we have to talk about the drawbacks of plasmonics. So we talk about the good things of plasmonics, but we also have to mention the drawbacks of it. The first one being high losses. Now, remember how I said at one point that wherever you have metals, you will have resistive heating or ohmic losses. That is also true, of course, in plasmonics, and that is one of the major drawbacks of it. It has high power dissipation, meaning that you're not able to create really, really long waveguides with them. You're confined, you're restricted by the losses that metals bring into the picture. Aside from that, it is mostly not compatible with semiconductor technology used in modern circuits. And with this, I mean that you cannot simply integrate a plasmonic waveguide into, let's say, the electronic circuits, for example, that we have now. Now, even having an electronic and photonic circuit integrated together has brought its challenges. There are ways to get around it, of course, now that is possible. But when it comes to plasmonics, things get a bit more complicated. So that's just something to keep into account. And one of the main reasons why plasmonics is still not a field that's really integrated into our everyday life, such as optical fibers and other electronic circuits. We can go into the review of our paper. Now, at this point, I hope we are all comfortable or at least have basic understanding of what a Kerr nonlinearity is. So remember changing the refractive index, as well as we already seen what plasmonic waveguides are. Now, in this paper, there's a lot that's going on in terms of what they're reporting. They report very important things, but we're not going to cover all of them. We're going to specifically focus on one of the things that they're trying to tell us. I'm more than happy to talk about this with anybody if anybody's interested later on, but let's start by dissecting our abstract.
So actually, before we dive into this interesting paper, I thought we can take a few minutes break.
Yes, I was gonna, yeah.
So in this break, normally we either talk about the concepts or if anyone in the audience have any questions, feel free to ask. So I wanted to recap. So why is non-linearity important in the context of photonics and plasmonics?
Now, remember, well, not only with this our platform, so with plasmonics and photonic systems, we're trying to exploit these nonlinearities because it is through these nonlinearities that we're actually able to get the ultra-fast processing signals that we want, right? It is through those effects that we're able to make data processing faster, pretty much that. So just want to think of it that way. Oh no, I was just gonna say, specifically for quantum computing, it is these effects that allow you to make the computations that you need with such computers. So yeah.
Hey, does anybody else have any questions?
Yes, of course. So you can think of a waveguide. Waveguides are just structures that allow us to guide light. Okay, so they allow us to guide light how we want. In the case of plasmonics, they allow us to guide light through the principle of total internal reflection.
I'll just repeat the question. So the question is, can you
Uh-huh.
please remind us what the waveguides are, or is it any structure that guides light?
Yeah, in general, it would be any structure that guides light. So, for example, we have optical fibers, right? That is a type of waveguide. In electronics, you can have waveguides, of course, different principles, but they're guiding, well, sorry, they're not guiding light in that case, right? Of course, they're guiding electric current, but waveguide is just, in the case of optics, I would just say anything that allows you to guide light. Optical fibers, integrated wave, even if you have, for example, I don't know if you've ever tried to shine a laser to a piece of like a crystal you can see the principle of total internal reflection, and that for a short period of time will act as a waveguide.
And basically, the goal of the waveguide in photonics and plasmonic system, the idea is to guide light as efficiently as you can, right? And that's why we have
Yes.
to talk so much about propagation laws. So my question is, so what is propagation? Is it just another term of saying that the light is traveling through some
Yeah,
medium?
so I guess up to that I just wanted that we wanted to propagate through it because we want high matter light interactions, right? You want your photons to interact with your material because that is what generates the nonlinearities, right? So you want the most out of that. Now, in some cases, as we'll see right now in this paper, you do not need very long propagation lengths to actually obtain those nonlinearities, right? You can have shorter, but in general, you want your light to travel for as long as possible. Not as long as possible, but as long as a length specifically, I think this will answer in this paper specifically, an optimal length at which you have optimal nonlinearities. So that is what you want in terms of getting to propagate. And losses are, you can get losses not only in metals, but there's also losses in different types of materials, such as you can have something called two-photon absorption that appears in a lot of nonlinear materials too.
Great. We have another question. So a few slides ago, when you reintroduced plasmonics as a combination of electronics and photonics, in that graph, what is the last quadrant?
Oh, that would be all technology, like all type of electronics. So in this would be here all the electronics where you have really slow processing speeds and you cannot make them really confined. So think of those like really chunky boards of electronics that you saw maybe your grandparents or parents have some.
Multiple.
Yeah, but like actually give me 1 second. I can show you one example. Not as chunky as this. This I think would be considered like really modern, but here I have an example just to show you of a PCB. Yeah, breadboards. Yeah, exactly. So like something like this, although it has really small components, I would still considering you can think of this as being more in this quadrant, whereas the electronics that I'm talking about here, as you can see, are in the nanometer, hundreds of nanometer scale. This is not in the hundreds of nanometer scale, so it would be considered in this region, um, mainly. So yeah.
So the
So
electronics is basically the chips in our laptops, right? That's electronics.
yes, exactly. So the chips on your laptops and your phones. Those would be electronics. It is a bit harder now. Photonics right now, or at least a few years ago, is going through the same phase as electronic was like 50 years ago, where you just got started. That is where photonics is at the phase right now. I would say right now, currently, it's a little bit more advanced. Of course, you have optical fibers, telecommunications is starting to rise up. There's a lot of companies that are prioritizing to do that. Now, when it comes to that, there's a lot of constraints to consider. So it's not as straightforward, but it's not as industrialized as electronics, but it's getting there.
Great. I guess we can continue on the paper.
First of all, we're gonna dissect our abstract, just a few parts of it. I'm just gonna highlight which are the main things that we're gonna talk about. This first part is just the part that is still of the abstract that is telling us why we care and pretty much a premise, right? The main thing that I want to mention here is that they say well, I think it's better just to read it. So plasmonic waveguides can greatly enhance nonlinear light-matter interactions through strong field confinement. So we've already talked about enhancing nonlinear interactions. However, achieving high-performance nonlinear plasmonic devices remains challenging because of optical losses and material damage. The main thing that I want to focus here is material damage. That is something that we mentioned, and is sometimes not mentioned in other types of literature. Okay. And the main thing that we're going to cover through this paper is, first of all, we're going to see how they investigate the ultimate Kerr nonlinear performance of plasmonic waveguides, which I just highlighted this to show you how the title pretty much spoiled the paper, the main point of the paper for us. But we're also going to cover one part specifically, which tells us that they are proposing, in this paper, they propose a concept of nonlinear effectiveness in order to quantify a mode's ability to exploit nonlinear material. So they're gonna give us a parameter, if you want to think about it that way, that is gonna allow us to tell us how good a mode's ability, so a mode, in case a plasmon mode, and in general the structure of our plasmonic waveguide, how good is it when it comes to exploiting nonlinear materials? Okay, so there is a bit more than this paper says. Okay, because as I said, it would be too long to actually cover all of it. More than happy to talk about it afterwards. But aside from that, I just want to highlight here once again that what this paper says specifically is that they account for optical damage. I keep repeating this because I think it's very important, is the fact that when you want to bring all the simulation type work into practice, so it's an experimental work, you have to account for things such as optical damage. And some papers in literature before do not account for this. Now, aside from that, the main thing that we're going to be exploring or just seeing, the main thing that they report in this paper is the fact that they find out that the maximum nonlinearity comes from metal dielectric metal structures. Okay, so remember the plasmonic waveguide structure that I showed you at the beginning. They find out that that is actually the best structure you can have if you want to have higher order nonlinearities. Okay, so those are the main things I want to highlight from this abstract. So let's get started by looking at the figures we have. Now, the first figure they introduce here is this here, which tells us the nonlinear phase shift per unit length relation to the input power. So how much power do you need to get such nonlinear phase shift? And at this point, I just want to mention that when I say nonlinear phase shift, I want you to think of it as being, well, it is proportional to the change in refractive index. Okay, so that is the relationship to the Kerr effect. Okay, so what is happening here? So I know there's a lot of things happening here, but let's take it one step at a time. First of all, we have bulk. So what do they mean when they say bulk here? They mean large-scale nonlinear targets that are not confined. So instead of having your nonlinear material confined in a waveguide, as the case of the waveguide line, you just have it there. So just think of it as a crystal that you shine light and you try to get a nonlinearity out of that crystal. Okay, so aside from that, we have here other terms that are important to know. First of all, this gamma here, which we're going to consider the slope of our waveguide line here, it is what is known as the nonlinear coefficient. Okay, there's a similar definition here for our bulk type, nonlinear material, but we're just going to focus on this one. Okay, and ultimately, what this is trying to tell us is that waveguides are much better at harnessing nonlinearity. So waveguides are gonna, if we have our nonlinear material within a waveguide, you're able to get max nonlinearities at much lower power. So for example, in this space here, right? If you want such nonlinearity, you have to input much more power if you have a bulk type nonlinear material, whereas in waveguides, you need much less power. And remember that at the end of the day, you want to be efficient when it comes to power. And in some cases, the power that you need, for example, to reach this level of nonlinearity in a bulk type device, it is not something efficient and in sometimes not even doable. Okay, so that is the main thing to tell us here is that waveguides are the way to go if you want to harness nonlinearities. Okay, so that is just a reminder.
Can you explain what is bulk exactly?
Yes. Okay, so in this, when they say bulk, they're referring to nonlinear materials that are not confined. So they're not confined like waveguides. So you know how in waveguide we have our nonlinear material, we have our nonlinear material that it is pretty much sandwiched in most cases. But with bulk in general, you can just think of trying to get a nonlinear effect out of a crystal. That's how I try to imagine it. So you just have a crystal and you shine light to it and you try to get a nonlinearity out of it. It is not as efficient as if you put that material within a waveguide structure in general.
Right. Thank you.
Makes sense? So just as I was saying, so waveguides are the way to go if you want to harness nonlinearities. But why? Okay, so there's two main reasons for that. The first one being slow light effect that I'm going to explain in a bit, and the second one being high field confinement. So I think that's pretty self-explanatory. You're able to confine your field to a much smaller area, thus getting a higher nonlinearity. But so what is slow light effect? Now, slow light effect refers to the pretty self-explanatory by its name. You're pretty much slowing how light travels through your dielectric medium, and this happened because in plasmonic waveguides, remember, you have forward propagation of energy in your nonlinear dielectric. So in the middle, the energy of electric field is propagating to one side, while in the metal you have a backward propagation of energy. So you can see in the metal, as I said, your electric field will die out, but still, when you're at this closer to the surface, you're going to have some propagation that is going to have an opposite direction. So this electric field here will influence the one traveling in the middle, and it will make it slow down by a tiny bit. Okay, so, well, by a significant amount, I should say, actually. And this is going to allow you to have higher light matter interactions since your light is going to be more longer within that material, if that makes sense. So that's why a slow light effect will be proportional to having higher nonlinearities because you get more light matter interactions. Okay, now in this paper I mentioned that they explored different modes of plasmonic waveguides as well as different structures, right? Now, before showing you this here, first of all, we have our surface plasma polaritons that we saw beforehand. So you just have a dielectric and metal interface. And here, the red light is the imaginary part of the electric field propagating in the z direction. The z direction here refers to the direction of propagation of light. And here we have the real part of our electric field. We're not going to worry too much about the imaginary part. We're going to care about the real part. Now, once again, just to remind you, I as I previously mentioned, your electric field will die out in the metal. As you can see here, it's very, very tiny and dies out really fast, while it actually propagates in your dielectric material here. Okay? And as I just mentioned before, these are different modes that you can have in plasmonic waveguides and structures. And when I say modes, you can think of modes just as the same as the plasmonic modes, just as you think of longitudinal modes or transverse modes. So I'm sure some of you guys have seen this in some of your classes, but they're just analogous to this. And an example, just to be more clear, for example, in optical fibers, you have different modes, right? You have this is a fiber that is a single mode fiber. Okay, so light can only travel in one way, so it cannot bounce, it just goes straight through. And as you can see here, we have a point source. Well, this would be the cross section, right? This would be your transfer mode. That if you look at it, you can see how all the electric field is concentrated at the center. There is no constructive, destructive interference of light. While in a multi-mode, you actually get a bit of constructive, destructive interference when you have different ways in which light can actually move through your waveguide, and you get this type of mode. So this type of cross section when you look at it. Okay, so that is just to give you an idea of what I'm talking about when I say modes. Just as you have modes in the case of optical fibers, so photonics, you have different modes in plasmonics. I'm not going to dive too deep into this type of modes. And structures, the only thing that I want you to always consider is the metal dielectric metal structure here, specifically this mode, since it's the one that is going to be showing the most promise out of all of them. Okay, so this is what's just done to have something to compare it to, something to compare the metal dielectric metal waveguide to. Now, we're going to look into this nice spot here where there's a lot of things going on, but once again, we'll try to take it one step at a time. First of all is the optimal length. Okay, now the optimal length is pretty much also self-explanatory. It's the length that your waveguide has to be in order to get max nonlinearities. Okay, after that we have our normalized attenuation length. Okay, so attenuation length just refers to the length at which you start to see a significant reduction in your nonlinear effect, okay? And it is normalized specifically to consider our surface plasma polaritons, okay? So that's what the axis is. Then we have our axis that tells us change in nonlinear refractive index, okay? So pretty straightforward, we have already covered that. And finally, we have this value here. So what are these Fs? Now, these Fs that you see here are what are known as figure of merit, okay? They're just a way to quantify the performance of our structure. Now, this is one definition of a figure of merit. Throughout literature, you might encounter different types of figure of merit that try to quantify how good a plasmonic or in general any waveguide structure is. In this case, the figure of merit that we're going to be working on has three main terms. The first one being the nonlinear coefficient. So as we saw, that is just the slope that we had in our previous plot here. So nonlinear coefficient. Then it also takes into account the maximum input power. Now, this is why the paper was telling us that they consider the damaged threshold, because the figure of merit, so when they quantify how good the performance of a structure is, they take into account what is the maximum power that you can actually input to the system, to the structure, sorry. Finally, we have the attenuation length. I've already explained this. And just as a fun fact, well, more of a fun fact just to show you, there is a direct relation between our optimal length and attenuation length. And this derivation is done in an entirely different paper, but it turns out to be a factor of 1.1. Okay, so now that we know that this is our figure of merit, that is just normalized specifically for our surface plasma polariton modes, let's take a look at what we see here. Now, the values that you see here are the values of the width of whatever material you have in the middle. In this case, in the metal dielectric metal, it refers to the width of the dielectric material. So here 200 nanometers and here 800 nanometers. Okay, so once again, as I told you at the beginning, I just wanted to focus on this little square here. Now, compared to all the other types of modes, the ones that are performing the best at a lower optimal length are our metal dielectric metal waveguides. If you want to achieve such nonlinearity, you need a much lower length than you would need for other waveguides, such as, for example, the ones that are performing worse, that are the MDH here. Okay, so those are performing really bad in comparison to metal dielectric metals, and at least in this optimal length, they are the best. Okay, so they give you the highest change in linear effective index, thus have the higher figure of merit. Okay, so this interest in metal dielectric metals leads to the following studies that we're going to see here. And in this case, we're not only comparing them to different modes of plasmonics, but we're also going to be comparing them to a silicon slot waveguide. So now we're introducing a photonic waveguide into the picture to compare with our plasmonic waveguide. Okay, now the first plot that we have here gives us, so here we are going to see this value here with rho and L, which is just telling us a way is pretty much just a way to measure how effectively a waveguide can use the nonlinearity properties of a material without damaging it. So pretty much how good we can actually harness nonlinearity without damaging material. And a high rho value here means that you have to have a high electric energy confinement on nonlinear material. So the material is really good at confining your electrical energy. Okay, and once again here we can see that our MDM waveguide or MDM gap plasma modes are really good in terms of rho. So even when you squeeze the electric nonlinear material in our waveguides here, you get a really good value of rho. So this is mainly because, as I previously mentioned, in MDM waveguides, you have strong and uniform energy confinement. And uniform just means that you do not have an electric field that's just oscillating like that. You have something that is uniform throughout your entire waveguide. So it allows you to keep good nonlinear values all through that waveguide. Okay, so that is what this first plot here is telling us. Then we go into the second plot here, which gives us a bit of insight in slow light effect. Okay, and just once again to highlight how good MDM waveguides are performing. Yes, this would be our short range surface plasmons here. They do perform better a tiny bit, but if you compare them in general, overall, our MDM waveguides still have a higher overall slow light effect. So that's another point towards showing how good MDM waveguides are. So higher slow light effect coefficient means that they are going to have higher nonlinearities. Okay, and finally, we have here a plot that is going to show us the nonlinear effectiveness. Okay, so this value was proposed in this paper to quantify how good your material is at getting nonlinearities. And here it takes into consideration three factors. Now this F here is just to consider losses. So it's in a way to quantify the losses that we get. We're not going to pay too much attention to it. Then we have our S, which is our slow light effect coefficient, and we have our rho here. Okay, so it's just telling us how much of a nonlinearity we can get without actually damaging our material. And with that said, before revealing what this plot actually looks like, considering this equation and what I've pretty much just been saying a lot when it comes to MDM waveguides, do you think that the MDM waveguide is going to have an overall high or low nonlinear effectiveness?
Hey, the question is, will MDM have an overall high or low EFF? So MDM is metal dielectric materials, is that correct?
Yes, metal electric metal.
Perhaps you should give a hint on how to
So think of so just looking so just looking at this equation without considering too much anything, just what I've said about the slow light effect in metal dielectric metal, as well as the rho value that we have here. Yes, high. Yeah, exactly. It will have a high nonlinear effectiveness. So overall, I'm just going to reveal the plot here. As you can see, overall, it will have a high nonlinear effectiveness because it has a high slow light effect, as well as a high rho value here. Now, something interesting to note is that the highest that it can actually reach is when the core, so the width of our dielectric material. Okay, so the width TC is the width. Sorry, I should have made that clear. Is the width of our dielectric material is very narrow, and I just wanted to take a kind of a look at this. It is telling us that when it is between 1 and 10 nanometers, it has the highest nonlinear effectiveness. Okay, so just to tell you how small that the size of the width of where we are actually confining our dielectric material is. And that is something important to consider, especially when you want to do experimental work, how hard this is to actually recreate. Now we're going on to the final values plots that we have. This we've seen before. This is just showing us why we're able to have a slow light effect in MDM waveguides. But this one here, this other plot here is pretty much shown to tell us that even when you have high absorption losses because of our metal, so when you approach the plasma wavelength is the max absorption wavelength that you're going to have of our metals. That is usually somewhere between somewhere here, so usually within the ultraviolet regime. The metal, even when you approach this place where you have high absorptions, your slow light effect and your nonlinear effectiveness will increase. So they're still pretty high. So all of this serves to just show the potential of plasmonics MDMs as very attractive platforms in nonlinear optical systems. Okay, it's nonlinear optical platforms, sorry, in terms of plasmonics. So overall, that is what they're telling us here. And that is one of the main messages this paper is trying to tell us, that MDM waveguides are the way to go if you're going to go through the plasmonic route. Even with really high losses, they still, as we saw here, are able to beat our plasmonics. So plasmonics, the nonlinear effective of plasmonic waveguide, sorry, of photonic waveguides are this purple here, whereas our MDM are this blue here. So they're able to beat photonic waveguides, and even with such high losses. So with that said, I know that was a bit intense last part, but I thank you all for following with this presentation. And yeah, thank you for coming.
Great. Thank you so much for that excellent introduction to linear and nonlinear optics. And I also think we have learned a lot about how lights interacts with matters within the photonics and plasmonic structures, and learn the physics principles behind plasmonics. So to encourage scientific discourse and reflection beyond the session, we have designed post-session activities, as you can see here. The questions will be posted on Discord shortly after the session, and I encourage everyone who attended the session live, or if you're watching via recording, that's great too. I hope you can join our Discord and answer questions. I hope it will challenge your thinking about plasmonic and photonics. Furthermore, since this is the last session, I wanted to talk about certificate of completion. So participants who attend all 4 sessions and complete the assignments and meet all the requirements will receive a certificate recognizing their effort and commitment. You can either attend live or watch the recordings on YouTube. There's no fixed deadline for completion, so as long as you review the materials, including the YouTube recordings, and finish the assignments for all sessions, regardless of the order, you will be eligible for a certificate. The goal, is to support your learning, research skill development, and critical thinking throughout the process. So if you complete all the assignments and requirements for all 4 sessions, and you submitted the information via email, which is complete, the verification process and feedback within 2 to 4 weeks. So this is the end of the session. Does anyone in the audience have questions?
Hi, yeah, I do. I just wanted to say really nice presentation, Livy. That was really nice.
Thank you.
My question is on that graph, that really complex looking one. I wanted to ask, what is attenuation length again? Like, could you explain?
Yes.
And is like lesser the better or something? Yeah.
Yes, I'm happy to answer that. I lost, where's the presentation? I am so sorry right now. Wait. Here?
Yeah, that one.
Is it this one? Yeah, no, so attenuation length is the length at which the attenuation becomes significant. Sorry, I should have made that more clear, right? So at one point where you actually start losing too much of your actual nonlinear effect of light in general, and you get something that's not significant anymore. So like you get significant attenuation pretty much.
So how does it relate to the optimal length again? Because there are 2 axes, I imagine.
Yes.
How do we?
There is an entire derivation of how this is true. But pretty much what is actually derived, it's a previous, like a prequel to this paper, which derives the fact that the optimal length is approximately 1.1 of the attenuation length. That makes sense. I can discuss this later in Discord if anybody's curious. I would have to review the paper, but yeah.
Right, that's great. If anybody else have any questions, feel free to just speak in the mic. I have some for you. So I know that you do plasmonics currently on for your research. So what got you interested in plasmonic in the first place?
Plasmonic came as a tag for me at least to photonics. So I was mainly interested in photonics and um, Plasmonics is inspired by photonics. So I got into looking at products in photonics, and also plasmonics is a field that it has been explored quite a bit, but still there's a lot of limitations when it comes to doing experiments within that field, and mainly model limitations. There's still a lot of work that can be done in it. So when I was introduced to plasmonics through photonics and realized that this is a field that still has a lot of potential in terms of experimental work, mainly because everything that I've shown you, like the paper part that I've shown you here, is done through simulations. And there is, if you look through the literature, there is actually a lot of simulation and theoretical work done in plasmonics and hybrid plasmonics, whereas there's not that much of experimental work done. And specifically, the project that I do focuses on the experimental side. So we actually want to prove that we actually get the same things that we saw in this paper in an actual experimental setup.
Yeah, so following up on that, I'm trying to imagine, so what kinds
Yeah.
of work do you actually do to conduct experiments on plasmon? Is this called experimental, this paper that you just showed today?
It does do simulation work. It
Okay.
doesn't have any like experimental like, in the fact of going into a lab and getting like data results, kind of experimental, but it is based on simulation work. And I would say very accurate simulation work since they do consider things that you would consider when you're trying to apply this to experimental work, right? That's why that's why as an experimentalist, I think I was really highlighting the fact that it's really good that this paper considered how much power you can have, right? Because you can do a simulation where you have really high nonlinearities, but then you realize that you're inputting too much power into your material, and if you try to do it in the real world, you burn it. So, um, in general, right now I'm just starting the work that I'm starting the PhD and everything, but my work would consist of going into the lab with this waveguide. So we have our waveguides, different types of waveguides that we're going to test, and we pretty much put it on a system that allows us to actually measure this nonlinearity. So you want to characterize how many nonlinearities you can have. You can usually when we test things, you test things with different lengths, right? So finding the optimal length and on all those parameters will sometimes be determined by experimental work, right? So you want to see that whatever you're getting in the lab is equivalent to what you get in the simulations.
Have there been a lot of experimental work on plasmonic, or is the literature mostly simulation based, would you say?
Uh, In plasmonics, there has been specifically, sorry, I should have said at the beginning that not much in the literature related to something such as in this paper. Okay, so exploring this paper specifically, getting something as narrow as, sorry, I just want to say here as in the 10 nanometer scale. Now this is limited in the past has been limited due to fabrication issues. There is a constraint of how now you can actually fabricate your waveguides and also consider how you actually get the nonlinear material within it. So there's constraints in that. Now, um, when it comes to literature that's a bit more new in terms of actually exploring, I would say, sorry, my mouse, I cannot see it, but exploring this, like the region that is highlighted here, there's very little in that sense of like exploring what happens when you have really, really narrow waveguides experimentally. There have been a lot of plasmonic materials, or sorry, nonlinear materials in plasmonics are explored, and there is experimental work done in that sense, but kind of getting to the limits here, that is something that's not widely explored.
Right. And can you go to that graph with the quadrant? So, I mean, here, the size of the devices. So I assume that photonics helps us create some kind of a very small nanoscale devices. Is that like pretty much the main advantage? You mentioned compact, right? Is that what it is?
Plasmonics, yeah, plasmonics does allows us to create the compact devices. In photonics, I did say it does get to the nanometer scale, yes, but if you are looking to do something in the telecommunication range, as I previously mentioned, at least in photonics, you're very constrained to not getting like you cannot get any. Oh, sorry, I don't know what happened. You cannot get smaller than half of your wavelength, right? So I guess that what you were trying to say is that the constraint of photonics, or can you repeat the question?
Yes, yes, I think you have
Uh,
answered my question. I just wanted to
oh,
clarify that the point of photonics to create a very small nanoscale compact device.
yeah, photonics, that is the purpose of photonics. Plasmonics, you can also achieve that, but you have to consider the restrictions that when working with light, you have diffraction limit, and that is, yeah. So whatever, every time you work with light, you have to consider that you have a limit on how small you can make things just because of the nature of light and how it diffracts, right? So the goal is to do that, yes, and the smaller you can make it, the better. That's why, and honestly, that's why I think plasmonics was inspired from, right? The fact that you're able to combine photonics, right, and also electronic systems to create surface plasma polaritons.
Great. I have one more question for you. So I know you mentioned slow light effect. So there's a slide, I think towards the end, that you explained, and I see that there were two
Yes, the lines.
the arrows were in two directions for different
Uh-huh.
materials. So can you explain what exactly are these arrows?
So the stars represent here would be, sorry, okay, now the energy of the electric field. So remember how I told you, how I mentioned when you have surface plus polarities, you have propagation of the electric field, right? And how this electric field propagates in the electric and the metal interfaces is different. In the metal, it propagates in an opposite direction that it does in the dielectric part, and it in the metal it dies out, as you can see here. It will not last for very long, just because you cannot have that electric field within your a conductor in general. Negative permittivity. Yeah.
So does energy determine the speed of light? Am I understanding that correctly?
You can think about it as sorry if I'm not explaining this way. Remember, the light is part of light is an electric field, right?
Right.
So you can think of it that way. Light is propagating one way, but if you have another electric field going the other way, right, it's gonna slow it. It's
Okay.
gonna slow it down. You can think of it that way, yeah.
Okay. Thank you so much for the lovely presentation, and thank you for the audience as well for your engagement with the talk. Thank you, and bye-bye.
Thank you so much, everybody. Have a great day. Bye.
Clematis Research Empowerment Hub. Empowering research for everyone.